Welcome, you curious mind, to the deep dive. Have you ever paused to wonder how the device you're listening to right now works? Or why a car battery eventually gives out? Or even how your own body manages to power itself minute by minute? Today, we're taking a deep dive into electrochemistry.
It's a really fascinating field, isn't it? It sits right at that intersection of electricity and, well, chemical reactions. We're going to explore the core principles that govern how electrons move, what that movement actually means for chemical transformations, and how these, fundamental concepts underpin everything from powering our cars to the very beats of our hearts.
Okay, so our mission today is to unpack the essential insights from a comprehensive look at electrochemistry. We want to make these complex ideas clear, relatable, maybe even a bit surprising without drowning you in jargon. So let's get into it. Right at the heart of electrochemistry, you mentioned redox reactions, oxidation reduction. When we talk about redox, what exactly is happening, like at the most basic level?
Okay, so at its simplest, a redox reaction is all about the transfer of electrons. Think of it like a trade. When an atom gives away electrons, its oxidation number goes up, becomes more positive. We say it's oxidized. And conversely, when it takes on electrons, its oxidation number goes down, becomes more negative. That's reduced.
So it's never just one thing losing electrons into thin air, right? If something gives them up, another substance has to be there to grab them. It's like a partnership.
Exactly. It's a fundamental partnership. And the terms can be a little tricky. The substance that causes another to be oxidized is called the oxidizing agent. But here's the twist. It gets reduced itself in the process, and the one that causes another to be reduced, that's the reducing agent, and it gets oxidized. There's a helpful mnemonic. Leo the lion says GER. Losing electrons is oxidation. Gaining electrons is reduction.
EO says GER. Okay, that helps.
Yeah.
Now, can you give us a really tangible example, something we might have seen?
Absolutely. Let's think about zinc metal reacting with acid. Maybe you did this in a school lab. You drop a piece of zinc into strong acid. What happens?
It dissolves, right, and bubbles form.
Exactly. The zinc metal atoms are losing electrons. They're being oxidized, going from neutral zinc to positive zinc ions. And the hydrogen ions from the acid, they're gaining those electrons, becoming neutral hydrogen gas, those bubbles. So they're reduced. It's a direct electron swap you can actually see.
Or even simpler things, like when you cut an apple and it turns brown. Or, much more complex, but respiration in our own bodies. That's redox too.
Absolutely. Rusting iron, that browning apple, breathing, they're all redox reactions happening constantly around us and inside us.
Okay, so electrons are moving, things are changing, oxidation states. But chemistry needs balance, right? How do chemists keep track of all this? Especially when reactions get complicated. It feels like balancing the books could be tricky.
It can be, but there's a systematic way using half reactions. Think of it like detailed accounting for electrons. We split the overall reaction into two parts. The oxidation part, where electrons are lost, and the reduction part, where electrons are gained. The crucial thing is making sure the number of electrons popping out in the oxidation step exactly matches the number going in during the reduction step. No electrons left behind.
And you're balancing not just the atoms, but the electrical charge as well.
Precisely. You have to balance both mass and charge. It involves adding things like water molecules or H+ ions if it's an acid or OH ions if it's in a basic solution. But the end goal is always the same. Atoms are conserved and electrons lost equal electrons gained. It makes these complex reactions predictable.
All right, so we understand the electron dance. Now, how do we actually use that energy? I'm thinking of those classic stories, Galvani and the twitching frog legs, or Volta building the first battery.
Yeah, those were absolutely pivotal moments. A voltaic cell or galvanic cell, same thing, is basically a clever setup. It captures the energy released from a spontaneous redox reaction. But instead of the electrons just jumping directly between chemicals and releasing heat, they're forced to take a detour through an external circuit, like a wire. And that flow is electricity we can use.
So the trick is separating the oxidation and reduction parts into different compartments, these half cells. Where does the action happen, the current generation?
It happens at the electrodes. And here's a key definition. Oxidation always happens at the anode. Always. And reduction always happens at the cathode. So in that classic zinc-copper cell example, zinc metal is the anode. It gets oxidized, releasing electrons. Those electrons travel through the wire to the copper cathode, where copper ions swim up, grab the electrons, and get reduced, plating onto the electrode as copper metal.
Okay, but wouldn't charge build up? Like the anode side getting positives and the cathode side negative, wouldn't that stop the flow? You need something else, right? Like a salt bridge.
Absolutely critical. The salt bridge is like the internal pathway. It allows ions to move between the half cells to keep everything electrically neutral. Without it, the charge imbalance would quickly stop the electron flow. Positive ions, catechations, move towards the cathode, and negative ions, anions, move towards the anode, completing the circuit internally. This continuous loop, electrons outside, ions inside, is the electrical current. And interestingly, in these voltaic cells, the anode, where electrons originate, gets the negative sign, and the cathode, where they go, gets the positive sign. It shows the direction of spontaneous flow.
That makes sense. It's like electrical pressure. So how do we measure that push? Is there a way to quantify it? You used the analogy of water flowing downhill earlier. Is it like measuring the height of the hill?
That's a perfect way to think about it. Electrons spontaneously flow from a state of higher electrical potential energy at the anode to lower potential energy at the cathode. This difference in potential energy per unit charge is what we call the cell potential, or sometimes electromotive force, M for short. We measure it in volts. So volts are basically the electrical pressure driving the electrons.
Okay, volts. And you often hear about standard conditions in chemistry. What does that mean here? Is it just standard temperature and pressure?
It's very specific for electrochemistry. Standard conditions mean 25 degrees Celsius, all solutions are at 1 molar concentration, and if any gases are involved, they're at 100 kilopascals pressure. When we measure the cell potential under these exact conditions, we call it the standard cell potential, and we write it as E degrees, E naught cell.
Got it. But how do we figure out these E degree values? There must be thousands of possible reactions. Do we measure every single one?
No, that would be impossible. We use a clever reference system based on standard reduction potentials, E degrees. These measure the tendency for a specific half reaction, written as a reduction, to occur. By international agreement, one specific half reaction, the reduction of hydrogen ions, H+, to hydrogen gas, H2, is assigned a standard reduction potential of exactly 0 volts. This happens at a special setup called the standard hydrogen electrode, or SHE.
So everything else is measured relative to that hydrogen reaction, like a benchmark.
Exactly. It's the 0 point on our scale. So a substance with a positive E degree value is easier to reduce than H+ ions. It really wants those electrons, making it a strong oxidizing agent. Conversely, a substance with a negative E degree value is harder to reduce than H+. It prefers to be oxidized, making it a good reducing agent. And to find the overall standard cell potential, E degree, you just take the standard reduction potential of the cathode, where reduction happens, and subtract the standard reduction potential of the anode, where oxidation happens, but we use its reduction potential value. If the resulting E degrees is positive, the reaction is spontaneous under standard conditions.
Okay, positive E degree cell means spontaneous. That clicks. Now, how does this connect to other big ideas in chemistry, like Gibbs free energy, the spontaneity measure,
Yeah.
and equilibrium?
Ah, yes. There's a beautiful direct link. The change in Gibbs free energy, G, which tells us if a process is spontaneous, is directly proportional to the cell potential, E. The equation is G exists NFE. N is the number of moles of electrons transferred in the balanced redox reaction. F is the Faraday constant. It's a huge number, representing the charge of 1 mole of electrons. So, look at the equation. If E is positive spontaneous cell, then Ag must be negative, which also means spontaneous. It connects perfectly.
That's a great connection. So GG links potential to spontaneity. What about equilibrium? Where does K fit in?
Well, G is also related to the equilibrium constant, K. You might remember G degrees is related to A degrees, and A degree is related to K. We can link all three: cell potential, free energy, and the equilibrium constant. Knowing any one of them under standard conditions lets you calculate the other two. It tells you not just if a reaction goes, but how far it goes before reaching equilibrium.
Thinking about real-world stuff. This makes me think about electric vehicles again. Our source material mentioned that lithium-ion battery costs dropped like 600% since 2010. That's huge. And EV engines are way more efficient, right? Like 70% versus maybe 15–20% for gasoline?
Exactly. And the reason for that efficiency gap comes straight back to electrochemistry. Electric cars convert chemical energy directly into electrical energy to turn the wheels. Very few steps, relatively efficient. Internal combustion engines, they burn fuel, chemical to thermal, use that heat to expand gases, thermal to mechanical. There are significant energy losses, mostly as heat, at each step governed by thermodynamics. That direct chemical to electrical conversion in a battery is just inherently more efficient thanks to harnessing that spontaneous redox reaction we talked about.
Okay, but batteries don't last forever. They run down. That standard potential, U degrees, must change as the battery is used, right? It's not always 1M concentrations.
Precisely. Standard conditions are just a reference point. In the real world, concentrations change. That's where the Nernst equation becomes essential. It lets us calculate the cell potential, E, under non-standard conditions when concentrations aren't 1 m or pressures aren't 100 kPa. As a battery discharges, reactants get used up, their concentrations decrease. Products build up, their concentrations increase. These changes affect the reaction quotient, Q, which is part of the Nernst equation. And as Q changes, the cell potential, E, gradually drops. Eventually, E reaches zero. That means the reaction has reached equilibrium. The battery is dead.
So the Nernst equation tells us that if you could, say, increase reactant concentrations or remove products, you could actually boost the voltage.
You could, for a time anyway. This is the principle behind something called concentration cells. These are neat cells where both half cells use the same chemical species, but at different concentrations. The voltage difference arises only because of that concentration gradient, and the cell runs until the concentrations equalize.
That's fascinating. And it's not just batteries. The source mentions pH meters. They work like this. And even biology. Nerve cells generating potentials because of different ion concentrations inside out. And electric eels using stacks of cells to create a big potential difference.
Exactly. A pH meter has an electrode sensitive to H+ concentration, essentially acting like 1/2 of a concentration cell. Nerve impulse transmission relies on potential differences across cell membranes caused by gradients of sodium and potassium ions. And yes, electric eels have specialized cells called electrocytes stacked in series, like batteries, to generate stunning voltages, even our heartbeat. It's regulated by carefully controlled changes in ion concentrations across heart muscle cell membranes, creating electrical potentials that drive the contraction. Electrochemistry is truly fundamental to life.
Okay, let's circle back to batteries specifically. We use them constantly. How do they fit into this voltaic cell picture?
Batteries are just practical, portable voltaic cells, or often multiple cells connected in series to get a higher voltage. We usually divide them into primary cells, your typical disposable alkaline batteries, which are non-rechargeable. The reaction runs once, then it's done. And secondary cells, which are rechargeable. Think car batteries, phone batteries.
Right, the throwaway alkaline versus the lead-acid battery in a car.
Exactly. The alkaline uses zinc and manganese dioxide. The lead-acid battery uses lead and lead dioxide electrodes in sulfuric acid. The key for rechargeability is that the products of the reaction stick to the electrodes, so when you apply an external voltage, you can force the reaction to run in reverse, regenerating the reactants.
And looking at modern tech, what's the big deal with lithium-ion batteries? Why are they everywhere?
Lithium-ion is revolutionary, mainly because of lithium itself. It's incredibly lightweight, the third lightest element, and it has a very, very negative standard reduction potential. It really wants to be oxidized. This combination means Li-ion batteries have high energy density, lots of energy for their weight, and produce a high voltage per cell, around 3.7 volts typically. That's way higher than older chemistries like nickel-cadmium.
That explains the power in our small devices. But the source mentions some safety history, right? And shifts in the materials used.
Yes, that's been an area of intense research. Early Li-ion batteries often use lithium cobalt oxide, like O2 cathodes. High capacity, but under certain conditions, they could overheat thermal runaway. So newer designs often use alternatives like lithium manganese spinel, Li-2O4, or formulations with nickel and manganese. These tend to be safer, more stable, and better for the environment, even if the energy density is sometimes slightly lower. It's an ongoing optimization process.
Okay, what about fuel cells? They sound similar to batteries, but aren't quite the same.
Similar principle, chemical energy to electrical energy via redox, but different operation. A battery stores its reactants inside. A fuel cell has reactants, like hydrogen and oxygen, continuously fed in from outside. As long as you supply fuel, it produces electricity. They're generally more efficient than combustion engines, potentially much cleaner. Water is the main byproduct of H2O2 cells. But there are still challenges, like the cost of catalysts, often platinum, and storing fuels like hydrogen safely and compactly.
Right, so not all these reactions are ones we want happening. Let's talk about corrosion, rust. Why is it such a problem, and how does electrochemistry explain it?
Corrosion is basically electrochemistry gone wrong, from our perspective. It's a spontaneous redox reaction that degrades metals. Rusting of iron is the classic example, and the economic cost is staggering. Think of all the money spent replacing rusted cars, bridges, pipes. One figure mentioned was up to 20% of U.S. iron production just goes to replacement.
Wow. So what's actually happening chemically when iron rusts? Is it just iron plus oxygen?
It needs oxygen and water. It's actually a mini electrochemical cell set up on the iron surface itself. Some spots act as the anode, where iron metal gets oxidized to iron ions, Fu2+, releasing electrons. Those electrons travel through the metal to other spots acting as the cathode, where oxygen dissolved in the water gets reduced, using those electrons. Then, the Fu2+ ions can get further oxidized by oxygen to F3 plus Xa, which combines with water to form hydrated iron oxide, that flaky reddish-brown stuff we call rust.
And things like salt or acid make it worse.
Definitely. Acid, lower pH, helps the oxygen reduction step at the cathode go faster. And salts dissolved in the water act like the electrolyte in a battery or a salt bridge. They help conduct ions, completing the electrochemical circuit and speeding the whole process up. That's why cars rust faster where roads are salted in winter.
So how do we fight rust using electrochemistry, besides just painting it?
Painting is a barrier, yeah, but if it gets scratched, rust starts underneath. A smarter way is cathodic protection. Take galvanized iron, it's iron coated with zinc. Zinc is more easily oxidized than iron, its E-degree red is more negative. So if the coating is scratched and both metals are exposed to water and oxygen, the zinc corrodes instead of the iron. The zinc acts as a sacrificial anode, protecting the iron cathode. They do the same thing for pipelines or ship hulls, attaching big blocks of magnesium or zinc that corrode away, sacrificing themselves to save the steel.
Very clever. Okay, last big topic. We've talked about spontaneous reactions making electricity. Can we reverse that? Use electricity to make a reaction happen, one that wouldn't happen on its own.
Absolutely. That's the whole principle of electrolysis. It happens in an electrolytic cell.
Mhm.
You use an external power source, a battery, a power supply, to provide the energy needed to drive a non-spontaneous redox reaction. Think about making really reactive metals like sodium or aluminum. They don't exist naturally as metals. They're found as ions in compounds. Electrolysis is how we force them back into their metallic state. Or electroplating, putting a thin layer of, say, chromium or nickel onto a cheaper metal object.
So it's the opposite of a voltaic cell, using energy input instead of getting energy output.
Exactly. You're pushing the electrons in the wrong direction, uphill in terms of energy. The definitions of anode, oxidation, and cathode reduction stay the same, but the polarity reverses compared to a voltaic cell because the external source is dictating the electron flow.
And can you predict how much product you'll make? Is it related to the amount of electricity used?
Yes, it's completely quantitative, thanks to Michael Faraday's work. The balanced half reaction tells you how many moles of electrons are needed to produce 1 mole of product. We measure the total charge passed in coulombs, which is current in amperes multiplied by time in seconds. Using the Faraday constant charge per mole of electrons, you can calculate exactly how many moles and therefore how many grams of product you'll get for a certain amount of electricity. It's stoichiometry with electrons.
That reminds me of the aluminum story in the source material, the Hall-Héroult process, developed by 2 guys in their early 20s independently. And before that, aluminum was super expensive, like more than gold.
It's an amazing story. Aluminum oxide, aluminum melts at over 2,000 degrees C, far too high for practical electrolysis. Hall and Héroult discovered, again independently, that alumina dissolves in molten cryolite, another mineral. This mixture melts around 1,000 degrees C, making electrolysis feasible. It completely changed the game for aluminum, making it the common, inexpensive metal it is today. But it still takes a huge amount of electricity. That's why aluminum smelters are usually built near sources of cheap power, like hydroelectric dams. And it's also why recycling aluminum is so important. It only takes about 5% of the energy to recycle it, compared to making it from ore via electrolysis. Huge energy saving.
Wow. So from, the tiniest electron transfers in our cells to these massive industrial plants making aluminum. Electrochemistry really is everywhere. It's so much more than just thinking about batteries. It's fundamental to energy, materials, life itself.
It really is. It shows how understanding these core chemical principles, electron transfer, potentials, equilibrium, lets us not only understand the world, but also manipulate it in incredibly useful ways. And hopefully, unpacking it shows that even complex topics have clear, practical insights and really cool connections.
Absolutely. So the next time you plug in your phone, see an EV glide by, or just, feel your own heartbeat, maybe think back to this deep dive into electrochemistry. Hopefully you're feeling a little more informed and maybe even a bit more curious. Thanks so much for joining us on The Deep Dive.